Great to have Shai Ben-David here for our next speaker. We'll talk about when is clustering easy and should we care when it's not.
Right. So this is going to be, trying to adjust to the time of the day that I'm talking and the big amounts of information that you have already had to struggle with, and all kind of hard weightlifting that Manfred took you through. So it's going to be survey-ish, but it's going to be a survey with my kind of perspective over the results. And I'm going to address the main theme of this workshop, or the issue of what is when does learning become easy over easy data, but from the perspective of one particular problem. I think that the issue in itself is very wide, and so I'm going to focus on one particular problem, which is clustering. So the main kind of insight that you are trying to get is we have the pessimistic prediction of worst-case complexity theory, and on the other hand, we have success in practical applications. And this is kind of the major theme of this week. How do we account for this discrepancy between the worst-case pessimistic view and success in practice? And of course, the most conspicuous example of that is SAT. But we already had several talks about SAT, and I want to talk about how it reflects in clustering. So what approaches have we seen to trying to resolve this discrepancy? So one interesting approach is to focus on the algorithm, to pick an algorithm and try to understand why does this algorithm perform better than the theory predicts for this algorithm to perform. And I think that this is what is happening with smooth analysis. We fix an algorithm, and then we try to analyze under this new analysis of smooth the perturbations of the inputs, why this algorithm performs better than the theory predicts. We haven't seen much of this approach in this week so far, of focusing on an algorithm. What we have seen more is focusing on the input, trying to understand when are inputs easy. So I think the oldest approach in this category is parameterized complexity. You're trying to say there is some kind of parameter that controls the complexity, and maybe in reality the level of this parameter is small, and therefore we can handle the problem. And another one we saw with Shai yesterday, the notion of correlated instances. So maybe the instances that we get are correlated with each other in a way that helps us solve them simultaneously faster than we could have solved them, each of them, in separation. The kind of approach that I want to talk more about is a notion of data niceness. So we want to define a notion of data niceness that separates this niceness from the worst case examples, and try to see if we can explain the success in practice by claiming that in practice the data that we get is nice, and for nice data we have efficiency that doesn't violate the worst case complexity. Just note that there is yet a third approach that we also have seen this week, and I'll also relate to it a little bit, and that's trying to combine the two. Trying to combine assumptions about the data with picking your algorithm with the type of algorithm that you're going to use. So I think, to me, one of the most promising here is the statistical learning. We've seen several talks like this. So we assume the data is generated by a fixed probability distribution. We don't assume that we know this probability distribution, but we just assume that it's there. That's the environment. And now we use the learning algorithm to try to pick for every instance the best setting of the parameter of the algorithm, or the best algorithm, and so on. So we are kind of solving our problem using a learning algorithm, and so there is a special algorithm involved here, and we explain the success of this learning algorithm based on the assumption about the data, that the data is generated in some close to IID fashion from an unknown distribution, but fixed distribution. So that's kind of combining an assumption about the data with focusing on a specific algorithm. Here is the learning algorithms. So that's the kind of things that Kevin was talking about, and I guess you were also. Right. And then we can talk about data niceness that is tailored to a specific algorithm. So we will see one example of this, when our notion of data niceness is really tailored to show that a specific algorithm that people use in practice becomes easy on this data. So Avri mentioned this in the introductory talk, the work by Ostrovsky et al. And another approach is to talk about resource augmentation. So resource augmentation is somehow of taking a step outside of the frame that we've been usually discussing and saying the reason our algorithms succeed is because they have some extra information. It's not just the problem of input decision making or input search problem, but we have some extra information, and this extra information gives us the edge to overcome the worst case complexity. And so we will see examples of how, when does extra information, which we can assume that in many cases the algorithm can have access to, can solve this gap between the worst case complexity and the practical complexity. Okay, so that's the general framework in which my survey is taking place. And I want to focus on clustering tasks just to make it more concrete. It's hard to talk here in general about all possible decision or computational problems. Okay, so what I'm going to talk about is about notions of niceness of inputs that have been introduced for the clusterability, for clustering. So what kind of data is easy for clustering? And then I will talk a little bit about the resource augmentations, what kind of external resources on top of just having data and the need to cluster it, or data and metric and the need to cluster it, can be available, and how they can make our algorithms run faster. And at the end, I will have some suggestions of changing the question. That's something I learned from my supervisor. I had a world-renowned mathematician, Shelach, as a supervisor, and his basic advice was, when you're facing a hard problem and you try and you struggle with it and no progress, then change the problem. So maybe we should change the problem here a little bit. Okay, so let me start by the first issue I want to talk about is notions of niceness of input approach for clustering. And there has been quite a lot of work on this in recent years. So we want, what are the challenges? We want to find properties that characterize naturally occurring inputs. And that's kind of a difficult challenge. We want to say such inputs can occur in reality and others cannot. And then once we have a characterization of what may occur in reality, or maybe in a specific application, maybe in the context of model checking or some other application, we want to see, okay, can we have easy solutions for these naturally occurring? Because now we have carved out only a subset of the possible inputs, and maybe all the hard cases are left out. So can those be easy to solve? And then can we formally distinguish natural inputs from natural input in a task-specific? And even more ambitious is, can we find a generic definition that will distinguish naturally occurring data from arbitrary hard case potential examples? And I'll have a small hint in this direction, but I don't believe really that this is possible. Okay, so we are focusing on clustering. We know that the most common clustering objectives are NP hard to optimize, and all of them, like K-center, K-means, K-median, and Colin talked about it. Many of the clustering talks mentioned it. And we want to ask, does this hardness still apply when we restrict our attention to clusterable inputs? And there is a phrase that was coined by Danieli and Natilineal, Amit Danieli and Natilineal, and they say maybe it's the case that clustering is difficult only when it doesn't matter. So I will call this the CDNM thesis: clustering difficult, not matter. And we will try to see what do we need in order to support this thesis of Danieli and Lineal, that the problems that we care about are not hard for clustering, as opposed to the worst case. Okay, so just a caveat what I'm not going to address. I mean, I don't know if I need it in this audience, but clustering is a very wide issue, and there are many aspects of it, and I'm not aiming to talk about all aspects. So what I'm not talking about clustering as a density estimation tool. Clustering sometimes is used also for density estimation, for finding high density regions, connected regions of a probability distribution. That's not what I'm talking about. There's no natural notion of clusterability there. I'm not talking about generative model. There's a lot of work like on generative models. I think Anko worked on this, and Sanjeev, and I'm not talking about generative model. I'm talking about data that I don't know how it was generated. And I'm focusing on the case where your input is some data set and a metric over this data set and the goal number of clusters. So it's a very limited sub-area of clustering, but it will demonstrate the kind of themes that came up in this research. Okay, so what am I going to do? I want to define requirements of notions of clusterability. So we are trying to define a notion of natural data or clusterable data. I'll call it notions of clusterability. And we want those notions to help us support the clustering is difficult, not matter. So what do we need? So what requirements will we need in order to support this thesis? Then I will list various clusterability notions that have been proposed, many of them by people in this room, and I'll examine them in view of the requirements. I mean, if our goal is to show that clustering is hard only when it doesn't matter, to what extent those notions get us closer to this goal? Yes?
So I'm not sure. I mean, logically, I'm having a problem. So you could have decided to refute the thesis and look for requirements that allow you to refute it. So, I mean, right, the requirements you're looking for should be something you believe in. So why did you decide to sustain the thesis and not refute it? That's maybe.
Oh, because clustering is being done over and over again all the time in practice. So you want to say, I mean, it's there. You cannot ignore it. People run clustering algorithms. They're happy with the results. We cannot say it doesn't happen because we can't explain it. So I'm trying to find an explanation to what is happening in practice. And then I will consider, as I promised, the utility of access to some additional resources. And then I will talk about alternative direction for further research, what I coined before as change the problem. OK, so let's start with the requirements. So what do we want from a notion of clusterability that will support that it's easy when we care about it? So the first thing is it should be reasonable to assume that most, or at least a significant proportion, of the inputs that you care about in practice meet the clusterability assumption. So you want to assume that the practical instances meet your notion of natural inputs, because these are the inputs on which you want to explain why we do well. Of course, there is no way to guarantee this property, because you want to prove that I care about a future instance if and only if it satisfies all, and an instance is natural if and only if it meets this property. We don't know any kind of formal definition of natural that I can prove a theorem if and only if or anything like that. So we will not be able to prove it, but it can help us eliminate notions that are too restrictive. There can be a notion that people come up with and say this is clusterable, and you can immediately see if you examine it against your kind of intuition about natural data that it's too restrictive. So it will help us to eliminate notions rather than to verify notions. And finally, we can check such notions against a generative model. So if there are generative models that they believe that they reflect reality or approximate reality pretty well, and we have a notion of clusterability, then we can hope to see that with high probability, those generative models generate clusterable data. If those generative models really are approximating the instances that we see in reality. OK, so that's the first requirement. It should be reasonable to assume that most of the data we see in practice satisfy our requirement, our clusterability requirement. Of course, the second part of it is we want to show that there is an efficient algorithm that is guaranteed to succeed once we limit our attention to those nice data. We want to show that for natural data, we can solve it fast. We want to explain reality. So we want a notion of natural data, and we want to show that for this definition, we can have an efficient algorithm. So those are the two most important requirements. And the main of the open problem is, can we come up with a notion of clusterability that meets these two requirements? We will see more requirements later, but those are the most important requirements. Can we come up with a notion that will satisfy those requirements? And let me next list some aspects of well-clusterable data that people use in order to define notions of clusterability. So there could be many aspects of data that will render it clusterable. And the different definitions that have been proposed can be categorized by those kind of aspects that they focus on. So the first aspect is perturbation robustness. So what is the observation here? That many hardness proofs are based on the construction of highly sensitive gadgets. In order to show hardness, I mean, I don't know how many of you lived like me in the community in the 70s when the big game in town was proving that something is NP hard. And then you just constructed gadgets. And that allowed you to do reductions of SAT or whatever to your problem. And those gadgets are very carefully crafted. And if you perturb them a little bit, usually they will no longer be serve the problem of showing hardness. So maybe that's the reason. So maybe in such gadgets, small input perturbation will lead to a significant change of the induced optimal solution. So maybe the idea that to define clusterability is to say natural data is robust to small perturbations, which distinguishes it from the examples that we construct to show NP hardness. I mean, this is something I should ask Uri. He's still, I think, for me, the master of hardness results. Okay, so is this really the source of input hardness? And do real input really fail to have this sensitivity to small perturbations? So that's one aspect, the first aspect. Already along this aspect, we can have different notions of clusterability, and I will just show two approaches under this perturbation robustness. So the first one is additive perturbation robustness. So in additive perturbation robustness, what I want to say is that your data is such that assume that our data is always a subset of Rn. So it lives inside some big metric space. And then if we perturb the data additively a little bit, so there is some kind of a parameter eta, every point is allowed to be moved by at most eta, we want that such perturbation will not change the optimal partitioning of the optimal clustering. So this is motivated by the idea of measurements errors. In reality, when you get your data, there are always measurements errors. Measurements errors are usually additive, not multiplicative. So you want to say, my additive errors should not really affect my outcome in real data. So this idea was first, I think, proposed. I mean, we proposed it in 2000 to show that under such an assumption, linear learning of linear classifiers in diagnostic case becomes easy. Otherwise, it's NP hard. And then in 2009, with Rita Ackerman, we showed that this also allows you to do k-means clustering and all kinds of center-based clustering, overcoming NP hardness with this additive robustness. And then in 2010, there was a paper that got a lot of attention by Bilu and Lineal that proposed multiplicative robustness. So multiplicative robustness does not have to assume that the data lives in Rn. You just look at all the pairwise distances, and you want to say that the perturbation of the data is such that every pairwise distance is multiplied by some bounded factor. So it allows you to make big changes to far away points, but only small changes to close points. So those are two different notions of perturbation robustness, and each of them leads to some different notion of clusterability. Yes?
So it's a very strict definition of the change in the output. It can't change the output.
No. So both of them can be relaxed.
Yeah.
You can look at it as a kind of a Lipschitz function, by how much small change in the input affects the change in the output. So you need a measure of distance between output, distance between clusterings, and distance between sets of points in the input. Right. So I'm presenting it as a 0, 1, robust or not robust, but there could be a parameter, sliding parameter here. Yeah. But I think the point to note is both definitions talk about the optimal clustering. The optimal clustering doesn't change due to perturbations. There could be other clusterings that small perturbations will change them a lot. You care about the optimal clustering, and that's kind of somehow a weak point because we never know what the optimal clustering is. Yes?
What about this sort of algorithmic stability type sort of robustness, meaning that you just replace one point with something else?
Right, like we do with learning.
With
Right, it doesn't fit with that because that's a property of the algorithm, and I'm focusing now on niceness properties of the data.
Yes, but you could just, but it's just a way of changing the data set. Like basically, instead of changing all of the points a little bit, you change one point a lot. So that's
Oh, I see what you're meaning.
Right?
Okay.
So how, you could.
Right, you could have defined it like that. I'm not familiar with such attempts in the literature. Right. Yeah, this is about changing. You're allowed to change every point by not so much. Right. Yeah. Okay, so this is the notion of perturbation robustness. Now there is another approach, a completely different approach to define what is clusterable data. And this approach was first introduced by Ostrovsky et al. in Stock, I think 2006. This is the journal version. And the idea is that you compare the cost, say k-means, you compare the cost of k-means clustering to the cost of k-minus 1 clusters. So what is happening here? If I have 3 clusters here for this data, then what is the cost of 3 means clustering? It's kind of the average distance of a point to its center when every blue blob has its own center. If I now try to compare it to the cost of just 2 means, so if I do 2 means, I just have to pick 2 centers. So something like this will become a center. And suddenly the average distance that was in this order becomes the average distance of that order. So the data is 3 clusterable if when you compare the cost of 3 clustering to the cost of 2 clustering, you see a big gap. So that's a very completely different notion of clusterability. You are k clusterable if when you moved from k minus 1 to k, you made a big progress towards reducing the cost of your clustering. With a similar philosophy, there's a kind of cleaner, in some sense, cleaner notions of Avrim and Awashti and Or, which is here. And so they define the notion of plus 1 plus 1 alpha weak deletion stability. And instead of comparing the optimal cost of k clustering to k minus 1 clustering, they just require that the cost of k clustering increases significantly if you try to merge any 2 of the clusters there. So you try to take all the points of one cluster and assign them to a center of another cluster. That will cause a big increase. So that's kind of the notion of stability that they use. You don't need to do the optimality of the k minus 1 means. You just have to compare, look at your optimal k means, and see how much it will cost you to merge 2 clusters. But it's basically the same philosophy. Data is k clusterable if there is a big gain by using k clusters rather than k minus 1. Yet another approach, and again by Avrim and Nina, who else was it? Was his Anupam was also on this. So luckily he's not here, so I could have forgot. Okay, yeah. So it's Balkan and Blam and Gupta, and they have a notion that, I call it uniqueness of optimum, and it says that, if you see these 4 blobs, they are not too clusterable. Why they're not too clusterable? Because you have 2 solutions, this one and this one, that both of them have optimal cost. Both of them have close to optimal cost, although in terms of the way they partition the points, they are very, very different. So we have this notion of uniqueness of optimum. That means if your cost is close to the cost of the optimal clustering, then also in terms of a partitioning, you should be close to the optimal clusterings. So you have here 2 parameters. One of them is by how much you're allowed to change the cost, and the other one is by how much it affects the change in the partitioning. Now, why is this a reasonable notion of clusterability? So I have an explanation which is different than the explanation that Avram gives in the paper. And my explanation goes through a notion of stability. So what is statistical stability? We somehow want to make sure that when we do clustering, we are not overfitting to the data. So how will we show that we are not overfitting to the data? We can take a sample of our data points and try to cluster this sample of data points. Then we can take an independent sample and try to cluster it again and ask, are we getting consistently a similar outcome? So that's the notion of statistical stability. It's like a notion of replicability of experiments. I'm doing 2 experiments with my data, picking a random subset, clustering it, repeating the experiment, do I get the same result? So a set is clustering stable if with high probability clustering 2 randomly drawn subsets result in a similar clustering. So it looks like a completely different approach. It's just kind of a statistical stability of the outcome that you got. However, we showed in a Cold paper in 2006 that data is clustering stable if and only if it has a unique solution, in the sense that Avri, Menina, and Gupta came with like 5 years later. So this notion of uniqueness of optimum corresponds to the very intuitive notion of statistical stability. So that's yet a different approach to a notion of defining what is clusterable data. Okay, so yet another more direct notion is the notion of alpha center stability. And this is, again, Pranjal and Avri Menina. And here what we say is yes, there's a question?
I have a question. So the first 2 notions that you presented, they also imply something about the uniqueness of the solution, right? Like perturbation resilience or...
Not necessarily. Not necessarily. Look at these four circles, 4 blobs. I mean, if you perturb the data a little bit, you still remain, if a solution was optimal before and you perturb the data a little bit, it remains optimal.
I see. So you didn't assume that the original thing was...
No, I didn't assume uniqueness there. I just assumed that that there exists an optimal solution that is robust to perturbations. And there was and we can show examples in which the exponential number of optimal solutions, and yet you get some kind of robustness. Okay, so this is a very direct notion, and here the notion is we take a point, and we take every point and compare its distance to its own center, to its distance to any center of a cluster where it doesn't reside. So we want to say that data is alpha center stable if for every point and every cluster Ci, even if I multiply the distance of x from its own center by alpha, it is still less than the distance of x from a foreign center. So every center has a much stronger affinity to its own, every point has a much stronger affinity to its own center than to any other center. So that's the notion of alpha center stability. So that's another approach to defining clusterability. So now we've seen several approaches to defining clusterability. These points are closer to their own cluster center by a factor of alpha more than to any other cluster center. And now we can ask, okay, so we have this wide collection of notions of clusterability. To what extent do they meet the requirements that we set for showing that clustering is easy when it matters? Okay, so all of them imply the existence of efficient clustering algorithms. Otherwise, there would not have been papers coming out of them. So all of them, the main work is to show that under these assumptions, you can get efficient clustering algorithms. The notion of additive perturbation robustness is weaker in the sense that the kind of efficiency that you get is efficiency in the dimension, but not efficiency in the number of clusters. So if you look at the hardness results, say on k-means for data in RD, we can show that even for fixed k, it is NP hard as a function of d, and even for fixed d, it is NP hard as a function of the number of clusters. So all the other notions, they handle both aspects of dependence on d. Sometimes they don't even require that you are in Rn, and dependence on the number of clusters. This notion only handles the dependence on the dimension, not the dependence on the number of clusters. It's a weaker notion. So all of them imply existence of efficiency, but I'm claiming that all of them, except this weaker notion that doesn't achieve as much, they seem to fail the requirements of being realistic. So now I'm making a strong statement. I'm telling Avram, your notion doesn't satisfy an important, I have to be able to support my claim. So how am I going to support my claim? So now I'm going to use something that Manfred promised he was not doing. I was going to show what is hidden in the O notation of these papers. Those are all stock Fox JCM papers. They are all using asymptotic notation. So when you try to check what is really the constant there, so for example, the epsilon separateness, it was the stock paper by Ostrovsky and Rabani. Where's your values? Not here. Okay, and Swami is here, right? He's also on this paper, and so the problem there is when you see when does efficiency kicks in, it kicks in only when the minimal between cluster centers distance is at least 200 times the average distance of a point from its own cluster center.
Wait, but below 200, they can't prove polytime, or they prove it?
I will get to this point. That's a very good question. Is it that below 200 they cannot prove, or it really fails? Right, I will get to this question a bit later. But at least if you look at the proofs, if you look at the current results,
I got the answer.
what is it?
I got a private answer.
Oh, okay. Then compare it with my answer and see if they are. Okay, so and now we can understand what I mean by not realistic data. In realistic data, you don't expect that the average distance of its point to its own cluster it's 200 times smaller than the distance to the next closest center. And that's where the efficiency kicks in. And another example, so that's the epsilon separateness. Another example is the uniqueness of optimum. And there, if you check exactly the parameters and the constants, you realize that you need that the distance of a point from any foreign cluster center is at least 20 times its distance to its own cluster center. So the proof somehow goes through this notion of center stability, and you can check what parameters of center stability you need, and you need for the proofs something like that. So and I will talk about the meaning of this pictorially in a minute.
I want to see the next slide.
What?
On average.
On average, right. And we can show same thing for the other notions for weak deletion stability and so on, right? Okay, so now to your question, is it provable or not? So most of those proofs go through this very straightforward notion of alpha center stability that show that if you meet my clusterability assumption, then every point, on the average, points are closer to their own center than to the next center. So what is the bound on the alpha on that notion of stability, which is core to the proofs? And here there is a result by Ben David and Raisin from 2014. And the reason I say Ben David, you usually don't say your own name, because it's not my result, it's my son's result. They show that when alpha is less than 2, then alpha center stable becomes NP hard. So this notion of alpha center stability cannot go below alpha equals 2. And alpha equals 2, I claim, is already not a very realistic requirement on real data. So if we want to look at alpha center stable, what does it mean? So I'm just drawing a picture here in one dimension because I cannot draw in more than one dimension. So assume that this is a cluster. So it could be that I have here dense points, and here the points are sparse, so the center will be here, if I do k-means. The center is closer to the dense area of the cluster. So now this point, its distance from the center is this size. So there can be no other center within 2 such steps, such a ball like this around this center should be clean of any other centers. So around any cluster, you have a big kind of ellipsoid that should be clean of any other centers, and the radius of this in every direction should be at least twice the distance of the furthest point to the center. So I'm claiming this makes this requirement feels that it doesn't capture all possible natural clustering applications. And this requirement is, we can prove that without it, if you go through alpha center stability, you hit NP hardness. Yes?
So this seems like a strong requirement in one dimension, but in high dimensions it's probably...
It gets worse. Because in every direction, you have to take this kind of, it's a big ball of empty of centers around your data that in every direction extends in the direction of the furthest point in that direction. In every direction, take the furthest point in that direction, look at this distance to the center, now go 3 steps like this, only then you're allowed to see another center. Okay, so the bottom line of the, yes?
So that NP hardness result, so basically you construct a single data set that is too stable, that is NP hard to cluster.
Right. Right.
But who cares about NP hardness?
Right, exactly. I mean, I thought that's what you were going to ask. So, right, because we are still taking somehow of a worst case complexity approach, but we limit ourselves to nice data. So I'm asking which notions of nice data, when you limit yourself to those notions, the hardness will not be as bad. That's the approach that I'm taking here. And as I explained at the beginning, there are different approaches to solve this dilemma, this discrepancy. Okay, so the bottom line of this part is there are proposed notions that are all provably they detect easy to cluster instances, but they do not capture all realistic inputs. And in some sense, in that respect, they're really not doing a satisfactory job. And somehow I feel that the current approach to define niceness, when you try to get efficiency in the number of clusters, when you try to be polynomial in the number of clusters, are kind of bound to fail. I mean, we do have a more natural notion, the additive perturbation, that we can show much stronger results. We need much smaller parameters, but it doesn't capture polynomial runtime in K, only polynomial runtime in the dimension. Okay, so let me move to the next part of my talk. I'll just mention other kind of less essential requirements. One requirement is a very nice requirement is maybe you want to show that commonly used algorithms become easy on your nice data. This will be important if you want to understand why we witness success. Because we witness success of clustering algorithm with some common algorithms. So can we show that with our clusterability, not only there exists an efficient algorithm, but the algorithms that we regularly use, it explains why they succeed. Like the success of Spielman and Tang in the notion of smoothed analysis. So from all those notions, only the epsilon separateness of Swami and Rabani, Ostrovsky, and Schulman, right, has this nice property. They explain success of the Lloyd, of a version of the Lloyd-K-means algorithm, which is the most common algorithm for K-means. All the others don't approach it. Another point worth noticing is that all of those notions talk about properties of the optimal clustering. And we never know what the optimal clustering is, so we don't have any fair way of verifying if when I give you a data set, it's a nice data set or not. Because you first have to find the optimal clustering. And you can run your algorithm and get some output, but you don't know if the output that you got is really the optimal one. Okay, so let me move on to the next step, which is resource augmentation. So is there any type of additional input information that can help us do the clustering, and maybe we have access to it when you're doing clustering in practice? So there are several notions that have been proposed. One of them is must link, don't link requirements on pairs of points. So you get on top of your data, which is a set of points and distances, you also get a list of pairs, must link and don't link. The extreme of this is a very nice notion of clustering of Avrim, which is correlation clustering. Well, for every pair of points, someone tells you those should be together, those should not be together, and you are trying to find the clustering that violates the minimum number of such requirements. But in many other cases, you have another objective, say k-means, but you have some input of some of the instances, some of the pairs you know they should be together or they should not be together. And we can think of many realistic situations in which you know such cases. Another kind of requirement, another kind of additional data is the merge split. Maybe it's again a paper of Avrim and Nina. Maybe you are communicating with the user and you present the clustering to them, and they'll tell you, oh, this cluster is too big, you must split it. Or those two clusters should be merged. So that's kind of the feedback that you get from the user. Another type of input that we're considering ways of communicating with the user to make the clustering more well-defined. So one way we were considering is give the user a small subset of their own data and ask them to cluster it and maybe learn from it how to cluster. So all of those approaches give you additional information that may direct the clustering. And I want to talk about one recent result that uses this type of information. And this is, we call it semi-supervised active clustering. Why semi-supervised? Because we get some supervision, we get some information in terms of which pairs should be together and which pairs should not be together. And it's active because the algorithm picks which pairs it wants advice on. And so we have this same cluster, different cluster over pairs of input points. And we show that few such queries, so order of k log n such queries, you have n data points, you want to cluster them into k sets, you make order of k log n pairwise queries, it can turn an NP-hard clustering problem into a problem that can be solvable in linear time. So that, I mean, I'm kind of asking the curious about other aspects of computational tasks in which you see such a phenomenon. You have an NP-hard problem, you make a few very simple queries, and with this oracle information, the problem becomes linear time solvable. Yes?
So is this for all instances of that NP-hard problem, or how do you set this up?
For every, you have an, I will show you in a minute more precise statement of the result. Okay, so here is a more precise. So we need a notion of clusterability here as well. And we have another notion of clusterability. I don't know how much time I still have.
Let's see what we have. We have 8 minutes.
8 minutes. Okay, so I will not, I mean, this is a different, slightly different notion of clusterability. What I don't really care about the exact definition. I have a parameter gamma here. The bigger gamma, the more clusterable the data is. So I have this notion of clusterability. And now a data set is k margin nice if the optimal solution satisfies this clusterability condition. And now we have the first theorem is kind of a phase transition phenomena. If this parameter is bigger than 2, then there exists polynomial time algorithm that will cluster your data nicely. We'll find the solution in polynomial time. If gamma is less than 2, then the problem is NP-hard. So with this parameter, we get a very sharp transition. If the parameter is bigger than 2, it's clusterable enough to have polynomial time algorithm. The minute the parameter is less than 2, the problem becomes NP-hard. So we have now there's no queries yet. There is no extra information. This is just how to solve the problem just as a clustering problem with this notion of clusterability, which is gamma margin clusterability that I didn't explain. Now comes the querying. So we design a probabilistic active semi-supervised algorithm that tries to classify under the gamma margin condition. It makes O of k log n queries. So the algorithm works, and every now and then it spits out a pair of points and asks, should these points be in the same cluster or not? And it does it only so many times. And it runs in time which is almost linear in n, n times k log n. And with high probability outputs the clustering C for every gamma bigger than 1. So remember, without the extra help, for a gamma less than 2, it was already NP-hard.
It was NP-hard when the number of clusters was large.
Both cases, the number of...
Small, then why can't
No, in most cases, the number of clusters is large. Of course. Yeah, the number of clusters in both cases for the hardness, here it can tolerate any number of clusters because you allow it more resources when the number of clusters grows. Right. So,
is this small constants or are you
What?
hiding constants here?
no, there are no bad constants here. Okay, so if you look at what happens when gamma is between 1 and 2, we see, so for gamma less than 2, it's already NP hard without the extra help. But all the way to gamma equals 1, where gamma equals 1 is just no requirement at all, you can solve the problem with few queries. The constant depends on gamma. The constant is like 1 of the gamma to the 4th, but it's not terrible. So it depends on this niceness of the data. Okay, so it's this kind of same cluster, not same cluster queries turns an NP-hard clustering problem into one that's solvable in polynomial time. I wonder if I prepared against the question, but I have it in my head. I don't know if I have it in my slide. Let's see what's happening. No, I don't have it in my slide. So the good question is people ask me, how will you answer such queries? Who will answer those queries for you? So really my motivation was an involvement in a project that people in the database group in our department work on, and this is data deduplication. So that's a real hard problem. You have records of patients, and they come from different hospitals with different clinics, and there are a lot of duplications. The same patient that was in this hospital and that hospital, but it was recorded slightly differently. Or in something that we see every day, if I go to Google Scholar and I look at the list of my papers, then I happily realize that I have 300 papers, although I don't recall having written so many of them. And the reason is that there are duplicates. They are recorded slightly different. And it becomes a real problem of industrial significance, how to do data deduplication of records. Now, in data deduplication of records, the user, usually if you show him 2 records and ask them, are they related to the same paper of yours or to 2 different papers? Or are these 2 records the same patient or not? They can answer you. The problem that hinders the user and asks them and makes them come to you and pay you money to do it for them is the size of the data. So it is a realistic setup. And okay, so I don't know if I have time to get into the basic, how much? 2 minutes. Okay, so I'll skip the basic algorithm idea, and I'll just say something about changing the question. So I propose to change the question in several ways. First of all the current approaches try to tackle the hardness of finding a minimal cost. But is it really what is required in practice? I mean, we know that in practice, users can never check if what you gave them back is the minimal cost clustering or not. So maybe they don't really care. Maybe we should define clustering computational tasks differently and not as aiming to get minimal cost. At least if what we are trying to reflect is what's happening in practice. So maybe we should start with the notion of meaningful clustering, and given a data set, output some meaningful clustering. How hard is this problem? I don't know. But that's a different formulation. It's not objective minimization, optimization problem. The other direction which I want to change is the need of alternative objective. Should we really care about exact number of clusters? So we see that hardness occurs when k is very big. The dependence of the number of clusters is what causes the hardness. But when k is very big, usually, often we don't care about the number of clusters. So the data deduplication is a good example of this. If we look at the record deduplication, we don't know in advance what's the correct number of clusters. What's the correct number of papers that I really wrote, and all the others are just duplicates. So how can we fix k in advance and try to optimize for a fixed k? And here there is a need for a different notion of success of clustering, and I don't have a good answer. One natural answer for people in machine learning is try to do regularization by the number of clusters, penalize for many clusters. But if you look again at record deduplication, you don't want to penalize for outputting many clusters. Maybe that's the correct answer. So I don't have answers to these questions. What are exactly better questions to reflect what happened in clustering in practice? I'm just claiming that we have to be aware that what we are analyzing in theory is not what people are searching for when they ask you to cluster data in practice. And there are tons of practical applications of clustering, so it's a worthwhile question. And okay, So can we come up with a formal objective that reflects the requirements of such many clusters applications? Some bigger scope questions: can similar approaches be applied to other worst-case problems? I talked only about clustering. Some of these considerations can be easily adapted to different hard problems. And another key problem: will the new analysis give rise to new useful algorithms? I mean, in all the successes of finding an efficient algorithm, we find algorithms, but these are not algorithms that people will use in practice. Will it lead us to new, insightful algorithms? Okay, thank you. Yeah.
Well, next speaker said.
Yeah, you didn't give us a sense of what that gamma nice algorithm
Okay,
is like.
gamma nice means
Is
that.
it a useful one?
No, I mean, it's as useful as any of the other notions.
I see.
But it's good for playing the game of showing how you can overcome the NP hardness. It's a notion that says a point is closer to members of its own cluster than to any member of another cluster.
And what is the algorithm that does it then when gamma is bigger than 2?
So the
The algorithm that solves it.
The query.
the algorithm for
Clustering.
clustering without the queries.
Yes.
I don't remember. I mean, I focus so much on
I see.
on finding the algorithm with the queries that I don't remember what was the algorithm without it.
We just go back.
Yeah.
So the active query case, the user sort of knows what the clustering is, and the machine is helping them to split things up nicely.
Right.
But clustering more generally is to find that structure to begin
What
with.
I'm saying is that clustering is very wide. In some applications, you're completely right. You don't know in advance. But in other applications, like this data deduplication, that was the motivation here, the user can tell you of every two records if they're the same patient or not. But they just cannot handle the amount of data. And that's why they want the algorithm.
Right. So I guess more generally, the not matter part of the equation, did you cover that?
Did I cover that? I mean, I did not, in this result, I did not relate to the aspects of even how natural is this condition that I still require. I still need some gamma in order to succeed, and I don't know how natural it is. But it just says that there is some separation between the distance of a point from other points which are duplicates to its distance to points which are not duplicates. That's the gamma factor. Yes?
So for the algorithm that uses the queries, what if the user gets like a constant number of the queries wrong?
Okay, we can handle this. So we have extensions to noisy answers, to faulty answers. All those are kind of, you can adapt to them. Yeah, it's a good question.
Anybody has a laptop that